Hello, everyone. After the semester is over, we still have two more origin seminars. One is today and one more next week. So today we have Sarah, our very own Sarah Moran, a wonderful origins organizer. So Sarah has received a bachelor's degree, honored, and PhD at Johns Hopkins University. And she's now director's postdoctoral fellow at University of Arizona at Planetary Science Department. But now, at the end of the summer, she is going to leave us and go to as a Goddard to start her Sagan Fellowship. So Sarah works on substellar atmospheres and also exoplanetary atmospheres with like the clouds and haze and interesting stuff in the atmosphere. So we'll hear about the multiple facets of silicate clouds in substellar atmospheres today. Sarah, take it away.
Thank you for that introduction. I'm using substellar here to mean both exoplanets and brown dwarfs, just things smaller than stars. And then facets you'll see come into play later because I'm making a terrible pun. I like what I'm doing. So first I'm going to briefly review just the history of what we know about silicate clouds, specifically in both brown dwarfs and in giant exoplanets, hot Jupiters. As I was building this talk, I was talking with Mark Marley, my advisor, and we kind of went down a little rabbit hole of the history, and I got very invested in it, and so I'm excited to tell you about it today. I'm going to go into a little more detail, specifically about silicon dioxide cloud features versus any other kind of silicate. Then we're going to talk about polymorphs of silicates, and this very much comes out of being here at LPL on the sort of cross-disciplinary department we have. And Sam Crossley, who I think is online, I saw, was chatting with Mark and pointed out that we're overlooking this thing that we really should probably be caring about. And so I'm going to tell you a little bit about that. I'll take that knowledge that we really should be applying and do a case study specifically of JWST-17b, which is a particular hot Jupiter with a silicon dioxide cloud detection. And then I'll talk briefly about places where I think that this research could go, things that need to be done, things that I just think are interesting, and I'm happy to take any questions kind of throughout as I go along, and then certainly at the end. So this is my favorite figure to show at the beginning of any talk I give, just because I think it's important to appreciate the beauty of clouds and hazes that shape our understanding of other worlds. So this is, of course, just a snapshot of the solar system. So from left to right, we've got Venus, Earth, Jupiter, Saturn, and Neptune. And so the predominant thing we see, at least in the visible, is all shaped by the different cloud layers that are active in each of these planets. And the composition of that cloud for each of these planets is dictated by the temperature structure of each of these worlds. That's true both for planets. And then if we look at brown dwarfs, this is a color magnitude diagram of the different types of substellar atmospheres from M dwarfs moving into L dwarfs to T, and then eventually to Y dwarfs. And you can see those arrows there are marking how these objects are placed in color space is dictated entirely by the kinds of clouds that are in their atmosphere. So as we move from M dwarfs to L dwarfs, we have the formation of mineral clouds, silicates. Eventually, those clouds sink below the observable atmosphere, and so we don't see them anymore. We get some clearing, which are what the T dwarfs we think are. And then we finally move down to even cooler atmospheres where maybe we get alkali cloud formation, and ultimately we get cold enough that we're actually seeing the very familiar water clouds in the Y dwarfs. And so now for your little history lesson, even before we knew that exoplanets existed, when brown dwarfs were still only a theory, we hadn't actually found any yet, there was this idea from both cosmochemistry and then from stellar atmospheric science that we should expect all kinds of condensates. That is, things that are gas transforming into either liquid or solid particles in these atmospheres. So this that I'm showing you is from 1965, and then a whole host of different potential condensates just based on simple thermodynamics of what should be stable at what temperature and pressure. If we move a little bit forward in time now, I'm showing you things from the 80s and 90s that this, I think everything here except for the last plot from Fegley and Lauders actually predates the first concrete discovery of a brown dwarf. So on the left there from 1986, we again see this figure where we're looking at pressure on the y-axis, temperature on the x-axis, and the dotted lines are different brown dwarf model atmospheres, and then those solid lines are the condensation curves of various species. So we see that the silicates are dominating here. And now if you turn your attention to the far right plot, we're looking again in temperature, pressure, space, but the axes are flipped now. And again, tracing out those different curves of where we expect things to be solid versus vapor, and also the chemical regimes that are dominating for particular atmospheres. So you can see Jupiter is sketched out there on the colder side, and then the brown dwarf GJ229b. What I thought was really interesting in doing this little history dive is this paper from Sharp and Hübner in 1990 that they highlight specifically, in spite of its refractory nature and the high abundances of oxygen and silicon, the most notable species that does not condense out is SiO2. So that idea kind of persisted for quite a long time in the literature, just because based on equilibrium chemistry alone, you do not expect silicon dioxide to condense out. So that's the theory side. On the observational side, we had evidence pretty much right away, as soon as we got observations of these objects, both brown dwarfs and hot Jupiters, that clouds were impacting what we see. So over there on the left, you're looking at data of, again, GJ229b, and you can see that it in the third down does not have strong absorption features through the optical and near infrared. Whereas if you look at the M dwarfs, you are seeing these strong lines from things like TiO. And so that was used as an inference of maybe these things are condensing out because this atmosphere is too cool. And so we're not seeing the gas phase particles of these. And then additionally, maybe we have some sort of solid particles that are actually blocking our view of any sort of gas. And then in the middle, we have the very famous first transmission spectrum of an exoplanet of HD 209458b. So that sodium line there, the dotted line, is what you'd expect from a clear atmosphere. And then the data are in the solid. You can see it's much more muted, that sodium feature, compared to what you'd expect. So that, again, was used to infer that there must be some sort of particles blocking our view high up in the atmosphere. And then finally, on the far right, we're looking at even just photometry, where you can compare the dotted lines, which are clear atmospheres, to the solid lines, which are cloudy atmospheres that seem to do a better job fitting the data, at least for this particular temperature in the middle there and at 1800 Kelvin. Again, right where we expect the silicates to start to condense out. So there's this idea that clouds are probably impacting things, but we actually got our first true sort of confirmation of that these clouds are probably made of silicate material with Spitzer, particularly when Spitzer was in its cryogenic era and we had all kinds of nice, lovely long wavelength data. So on the left there, you're looking at a sequence of L dwarfs, and highlighted there is the region where we think that the spectrum is being strongly impacted by silicate clouds. And then another kind of maybe more obvious comparison of that is on the right, again, with a few different L dwarfs, where you see that strong bump from 8 to 10 microns that, again, is probably due to silicate absorption. So these are both from Spitzer. The other thing that was recognized right away as soon as this was seen is that we should probably be able to tell the difference between amorphous silicates and crystalline silicates. And so on the top there, you're looking at both enstatite and forsterite, and then the bottom is just enstatite. And the comparison between those when you suddenly change the chemistry, you see that peak of the silicate bump moves a little bit, and then we should also be able to pick out the fine structure if it's indeed crystalline versus you get just sort of this blob if it's amorphous. And that matters because it's telling you how fast the vapor is transforming into this solid particle. That dictates the structure of the material that you're going to get out on the other side.
Can I ask a question?
Yes.
Okay, so we have, I mean, the identical features in photocatalysis, but the way we interpret this in nature of grains is if they are heated at very high temperatures. Is that the same yet?
So it kind of matters if you're thinking about a bottom-up or a top-down cloud formation process. So we're tending to think that it's like precipitating out of sort of a melt phase because it's coming from depth. In the bottom-up regime picture, you're picturing high pressure, high temperature, and then it's shifting to low pressure but still high temperature.
I see. And so that it depends then on how it cools.
So you're thinking about how it cools versus how it heats up.
Okay, cool.
If you don't hold with the bottom-up approach of cloud formation, you think more about a top-down, it could change. And that's also, I think, an important thing to consider here, which I'm not going to touch on too much after this, but I think that's a really good point, actually. It
So
matters.
cooling time matters too, right?
Yeah, both cooling and the heating time. So that's on the brown dwarf side, and then also in the hot Jupiter regime, we have a lot of evidence that clouds are shaping everything. This is a figure from Peter Gao in 2020. All of these little dots are sort of an average of a bunch of different hot Jupiter measurements, particularly with Hubble, in the 1.4 micron water band, and sort of just using that as a tracer of how strong that water band is to infer the level of clouds that are present in that atmosphere. And so part of this work was also running a whole series of theoretical models, including microphysical models. And so the thing that came out of that is that the thing that should really be dominating here are these silicates. You do have contributions from things like TiO and the aluminum oxides, but they're really not the largest component of the clouds that are impacting the spectrum that we see. Part of that is also due to just how easily these things nucleate. So in certainly the models that I use and more simple models, we kind of treat anything as like once you cross a condensation curve, you turn from vapor into a cloud particle. But there's some energy barrier that you need to overcome to make that phase change happen. And so what we're seeing here is just how efficient that nucleation process is as a function of different kinds of species. And so highlighted in yellow there is forsterite, which you can see is just really, really efficient at making this phase change. And so that's why it's able to so quickly make all these different kind of particles and why it's so dominant in the spectrum that we would expect to see. So this is all very nice. I mean, you might wish we could then take Spitzer and look for these silicate features that we would expect to see. By the time all of this kind of came together for the exoplanet literature, we no longer had cool Spitzer. It was the era of warm Spitzer, and so we didn't have access to those longer wavelengths where that silicate feature pops out. And so then this very much became all eyes were on JWST holding potential for making these kinds of measurements. And so in this plot, you're seeing again, a sort of scaled version of a transmission spectrum. So the y-axis there is some like scale height divided out version of a transit depth as a function of wavelength. And so you see in the blue there, this really enormous peak from enstatite, then maybe sort of a more muted contribution from the aluminum oxides, and maybe around 15 microns you might even pick out some other very high temperature materials, although that's kind of the edge of you can see highlighted there at the top, the low resolution spectrometer mode isn't really able to catch those high temperature species, but the proper silicate, the enstatite, is right broadly in the middle of that MIRI LRS mode. So that was sort of the picture at least up till 2020, that we should really expect enstatite and forsterite clouds. They seem to be really easy to make. We have evidence of these silicate features. And then from equilibrium chemistry, we just don't expect the silicates, the silicon dioxide by itself. And then this was kind of a big result then in 2021. This is from in particular Eldorf that I no longer remember the name of, but the data there are in black from like 3 to 4. And then you can kind of see the gap there. And then there's some more data from 5 to 14 microns. And various different models are overplotted. And this work was led by Ben Birmingham, and they did sort of an incredible number of different cloud parameterizations and combinations. I thought about putting the plot in here, but it would take up like the whole page, and then some of all the different permutations of what happens if you do an enstatite cloud plus a quartz cloud. What happens if you do a forsterite cloud plus a quartz cloud? What about if you add iron? And so like every possible combination that you could think of, also including amorphous versus silicon, amorphous versus crystalline particles, and this was their best fit. And so they infer that you also need, you get this very confident result that you need the quartz clouds in addition to the enstatite. And yes.
Is there a spectral feature for the clouds, or is it just, you add the clouds and then you see that the overall fits better? So is there a specific?
I hope online is my mouse. Where is my mouse? So here.
Okay. So that's
this is the
SiO2.
This is a combination of SiO2 and the enstatite. So
It's very wide.
they blend here. So you'll see, and some of the later. No, you don't, because I don't have any enstatite figures. I've lost the mouse now.
Okay. So it's around 8 microns.
Yeah, so this is a combination of those modes. And so that they found the best fit is a combination of these clouds. And you can see here, this is like a little cartoon version of where these cloud layers are. And so this is like the 1 sigma pressure levels of the clouds. So you have the enstatite just a little bit on top of this deeper quartz cloud. And then there's another iron cloud much further down at the bottom.
Do you know how they determined that particular cloud structure? Is the same thing? They just tried a bunch of.
Yeah, so they included all of the different species. They had a bunch of different particle size distributions that were just prescribed at different pressure levels. And so they had like a log normal distribution and a Hansen distribution. And again, I do not remember all of the different things they tried, but it's not self-consistent, it's prescribed, sort of like paint a cloud on with these properties.
Okay.
There's a question in chat. Would you like to look at it? So, the Gordon asked, Fred Hoyle wrote papers claiming diatoms in space. Could he have seen this SiO2 cloud?
I'm not familiar with what this is specifically talking about, so I'm not sure. Space is vague. Need a little more information than that, sorry. Diamonds.
Huh? Calcium, okay. Oh, Mark. Thank you, Mark.
Mark is there.
Yeah.
I'm sorry, I'm not familiar with this.
Diatoms are calciums. That's what Mark replied.
You're getting some suggestions.
Yeah. Hydrated is like 2.
That'd be opal.
Ah. Oh. Opals. Interesting.
Anyway, so this result kind of proved that maybe you do, I will look up his papers, thank you. That you also need to consider quartz in addition to enstatite and forsterite. So again, that was a brown dwarf. With JWST, we also got our first detection just last year of this particular species in a hot Jupiter. So this is WASP 17b. All of the infrared, near infrared, and optical data here is from Hubble, both from STIS and WIFC3 G141 and 102. And then over here, we have our JWST MIRI LRS mode. And so this is a best fit model from the Picasso and Virga framework, which I'll talk a little bit more about in a few minutes. And this is, they're just showing the best fit model here, that what they could infer. And this does contain specifically a quartz cloud. And so this is the pressure temperature space and the condensation curve. And so you have a metallicity dependence of where this is condensing out. So you'd imagine it'd be higher in this particular atmosphere if it was 1 times solar versus 50 times solar. And so they infer that it's like 80 times solar based on their retrieval analysis. And so you should be forming these particles maybe around a millibar. And so this is a version of a sort of contribution plot where on the top, you're seeing the spectrum as it would be if you took out that species. So this yellow is showing that if you don't put in this quartz cloud, you lose this bump that's very prominent in the spectrum. So that's their evidence that you are in fact seeing this quartz cloud. The other primary absorbers here are water, which is shown below, and then also carbon dioxide. And they could even do better than that, just saying that it's silicon dioxide. They actually do make a statement that they think it's quartz and not amorphous silica. And so they use this little zoom in right here where the yellow is the crystalline form, the quartz form, which is closer to the peak that they see in their spectrum compared to this slightly redward shifted amorphous form. You also get a pretty good handle on the particle sizes that you need to actually make this feature pop out. And so this is for a whole different range of particle size distributions where they can really pinpoint that you need something right about 20 to 40 nanometers here. And that affects both this silicon feature as well as the optical to near infrared slope. And so part of this is showing is that we can't just trust equilibrium chemistry alone to predict the kinds of cloud species that we should expect. And there is actually early work that did consider silicon dioxide clouds in particular, and that's Christiane Helling's work. And part of how they did that is that it's not equilibrium chemistry, that this is all cloud formation driven by dirty grains. So mixed phase cloud particles, usually using TiO or TiO2 as a cloud seed to actually start that process. And this actually is one of the more sort of top-down pictures of cloud formation versus a bottom-up. And then even more recently, because of these detections of silica, both in that L-dwarf as well as in WST17b, this paper just came out this year suggesting that maybe there's some sort of magnesium to silicon ratio that is driving what kind of particles you should be seeing. And then that also has, of course, implications for how you're depleting oxygen out of the gas phase as it gets tied up in these condensates. So we have this whole chemical picture now of how these species are condensing out of the atmosphere, but there's actually more to consider. And so that's when you bring in the idea of different crystalline forms of silicon dioxide, or really any material, as a function of temperature and pressure. And so there are actually multiple stable polymorphs of silicon dioxide at high temperature and low pressures. And so this is sort of a geologist plot. So it's pressure in kilobar, which is very alien to me, who thinks in millibars and microbars. And then temperature is in Celsius, but you can see quartz is down here below 500 C. And then you've got melt here, but all in between you have these two forms, cristabalite and tridymite. And so these are just different representations of the crystal structure that results when you have these different temperatures. And you can imagine that if the crystal structures are different, then the bond lengths are also different, so that's going to change their spectrum.
Are you constraining the temperatures from your observations that you are sure that you are in the high temperature regime?
This is very much a sort of toy model case study. So we're taking, as I move forward, we're taking the best fit temperature pressure profiles from other people's work and then just seeing does it match. I'm not self-consistently trying to predict yet based on this. That's where we're hopefully headed. So if we think about those particular pressures and temperatures, that puts us very solidly into this L dwarf regime where we're living right here where we expect these kinds of clouds. Illustrated by this nice cartoon where you see all the clouds in the atmosphere. And then I'm giving you a little cartoon here for a picture of tritomite. It looks super weird because the crystal structure is so different.
It looks really thin.
This is a thin section.
Just slice the section.
Yeah. But even then, like it looks very strange compared to how I think of quartz. So to break that down a little bit better, now I'm showing you again our favorite temperature pressure diagram with the dotted lines are the different condensation curves. Solid lines are different model atmospheres, and then I've shaded the different background regions where a particular polymorph should be dominant. So I've just basically drawn lines of these things are stable at 1 bar, and then I just carry that up to lower and lower pressures. It's just probably not totally legit, but it's good enough for our toy model. So we can see here that the initial phase that happens here is cristabolite, and then maybe the upper atmosphere of a couple of these objects, you end up in the tritomite phase. Maybe you eventually go to beta quartz, and then for the very coolest objects, maybe you're ending up with alpha quartz. So these particular pressure temperature profiles that I've drawn from here is WST 17b. This is just the best fit pressure temperature profile as reported in Grant et al. 2023. There's another paper that came out a little bit earlier for WST 107b, which is a Neptune-y kind of object. And yet they also see very strong evidence for silicates. And so I'm showing that in order for that condensation curve to get crossed, that you're actually very deep in the atmosphere here to make that happen, where they actually are observing the atmosphere around this pressure temperature. And then this L dwarf is actually the best fit from the Sonora grid that fit that Birmingham paper. So again, you're seeing just how things are crossing and where. So I already kind of mentioned this, but because of the different crystal structures, that means that the physical properties of these polymorphs are different. So on the x-axis, we're looking at density. So alpha quartz that people typically use is up here, but as you move to these higher temperature phases, they change, they get lower. So tritomite is actually the intermediate one, it's the lowest, and then the cristabolite is the high temperature, which is kind of in between. And then this is just the real refractive index that you can see also decreases basically according to density.
Sorry, what is the difference between the blue and the red?
So that's the red is a theoretical prediction from this paper, and then the blue is experimental data. So you can see there's some sort of offset here, but the trend is fairly consistent.
The offset is pretty consistent as well.
Yeah.
Yeah. I did not dig into why their theoretical predictions seem to be offset from the experimental work, but the trend is what I decided I cared about. So with this in hand, this knowledge that we should expect these polymorphs, we decided to see, can you actually observationally distinguish between these things? So to do that, I am using the Virga and Picasso modeling frameworks. So Virga is the cloud code side of things, and it's doing a just basically mass balance clouds. So again, you're assuming once you cross the condensation curve, you are turning vapor into particles. And then from there, you're just balancing basically upward mixing with the sedimentation efficiency of how fast particles are going to settle out of the atmosphere. So you find some balance where that balance happens is the cloud layer. And so then we're feeding that into Picasso, which is a radiative transfer code as well as a climate code. But again, for the climate, including the temperature, pressure, and the chemistry, I'm just taking the values that were already pre-computed for WST 17b. So the first thing we have to do is draw some optical properties from somewhere for me to feed into the cloud model. And this is sort of the major stopgap of where you have to start to make things up. So there is this nice paper from 2013 that measured cristabolite. And so this is the mass absorption coefficient, which you can translate to the imaginary refractive index, which is helpful. For tridymite, things are more dire. This is the paper I found with the longest wavelength coverage from 1958, which meant that I had to, data thief that plot, which has a weird scale bar, and I actually got fed up with doing it, and my husband did it for me because I got so annoyed. So there's full credit for that. There are more recent measurements of tridymite, but they cover a narrower wavelength range, and so I decided not to use them. Again, this is the transmission spectrum. And so from these two different measurements, we can get the absorptive component of the refractive index, but we don't actually have anything for the real refractive index. So now I'm just plotting here that data that I stole from these two papers with our imaginary refractive index. And so you can see the peak of this feature is shifted slightly for the tridymite, slightly bluer. The cristabolite actually almost plots exactly on top of the amorphous silicon. And then we have quartz here is in teal. And of course, we have nothing here for our real refractive index for these two polymorphs, which means I said that we improvised. That means I just actually tacked on the quartz in order to be able to put something into the model to make it go.
Sorry, I don't understand. So for the real component, you take the component of the quartz?
Yes, I just stitch on the quartz value because I don't have anything better to do. I tried just pretending it was completely non-scattering and completely absorptive. When you actually propagate that through to the spectra, it goes bananas. It makes no sense. So this is my intermediary step, is to just pretend it scatters exactly the same way as the quartz.
So the quartz work out the best.
I trust the quartz data the most. Not really the same thing. In a perfect world, I would have lab data that I could do this properly, but this is really much, demonstrating that we need to do this better. So when you do that, when you make up real refractive indices and then put it through a MIRI code, this is an example of the extinction efficiency. It's on the y-axis there as a function of wavelength for all of the different polytypes. It basically mirrors what we saw from the absorptive component, which is not surprising given what I fed it. But again, you just see this is for a particular particle size that we are actually separating this peak out. So then it's time to put it into the model. And what you see here is the turquoise or the quartz clouds as reported from Grant et al. The gold is the amorphous, again, same exact parameters as from Grant et al. And you can see that slight blue word shift of the peak for quartz, which is why they're able to basically pick out this particular data point that leads them to decide quartz is a better match. So this is for cristabolite in pink. It's slightly too red based on this. And this is, again, preliminary data. I have not actually run statistics against this. This is chi by eye fitting. Work in progress. But at least by this metric, cristabolite doesn't look like it's the greatest fit. So next we go to tridymite. It is capturing this peak better, but maybe is almost too blue based on how that peak is. So again, I actually have to run statistics on this to see what is in fact the best fit, but this maybe is promising that tritonite is doing a better job. So this is just accounting for the optical property differences. We're using the exact same condensation curve, we're using the exact same density in the mass balance calculation, which I've already told you was not right. So the next thing I did was change the density for each species and then again rerun the model. And you might look at these two and say they're basically identical, which is true. There's this very, very slight difference in the spectrum. You can maybe see like here, once you allow for the like lower density tritonite. Not so much. And that comes out, so now I'm just reminding you of the sequence of how things plot with density. So what we're looking at now is the mean particle radius that makes up the cloud layer as a function of pressure. You can see that they're basically identical here for each species. You're getting slightly bigger particles, very slightly. We can even zoom in a little bit here. And just like these are very minute differences in terms of the peak particle size at this pressure level. If you also think about just the cloud overall, you are getting slightly higher. The very top of the cloud layer is maybe slightly higher for these lower density species than for quartz, but again, it's not really noticeable. So that's what I have done so far, but I think there's a lot of different places we can take this work. So first of all, I want to apply this to an L dwarf. I haven't gotten to that yet, and I think it's going to take a little bit more tweaking just because the silicates should be forming at lower pressures, and so then getting them lofted up to the point where we actually can see the differences in the spectra may be challenging, but that's something that I'm actively working toward. I already touched on this, but this is the best I could do for tritonite and this initial run of models. And we have some more recent stuff here from 2000. And this is actually showing it as a function of different temperatures that actually measured the tritonite at different temperatures, which is great. But you'll notice that the units are just arbitrary units, which makes me nervous to, propagate that through the math that it takes to get to an imaginary refractive index, which is why I ended up going with the earlier one. So it'd be really great if we measured these properly at the phases we expect them, and then publish that.
Sorry, which lab is that from CTART?
I do not remember.
Because otherwise you could contact the authors to get.
That's true. 2000 is not so long ago. I looked at that and thought, are they still in the field? But that's probably my young person bias. I should think about that. That's a good idea.
Yeah.
Thank you.
I know some people in Jena who do this type of observations in Germany. So
Yeah, I mean, so it would be nicer to have broader wavelength coverage than this, but since this does capture the this in wave numbers, this is about the 8 to 10 micron region. So it's the part that we need.
But they might have done something newer.
That's
So I
also
want
true.
to contact with them.
And just didn't publish. Something that I think has real potential here that's definitely beyond this first little paper I'm doing is exactly this effect of, can we use these polymorphs as tracers through the atmosphere, both for vertical transport, also for how things are getting transported around the planet or the brown dwarf. And so this is an example, and all the purple is from Diana Powell and Ji Zhang. I don't even think this is published yet, it's just on arXiv, that they use a microphysical model with two-dimensional clouds and just how that changes the particle size distributions and where clouds are in the atmosphere. And so if you add in this additional aspect of being able to trace the different polymorphs, I think that could give you something really nice as a way of measuring temperature throughout the atmosphere, which I think is really exciting. Everything I've done so far has been imagining that these are perfect spherical particles to put into the MIRI code. But of course, because they are crystalline, that very likely is not true. And then additionally, you might expect that there are some weird inclusions that, at least with rocks, sodium and aluminum very frequently get incorporated into silica. And so how might that affect if these are in the clouds? So this is just an example of a MIRI code versus treating spherical, non-spherical aggregate particles, and that you really dramatically shift the peak and the amplitude of scattering and absorption and extinction. And then sort of even really pie in the sky, thinking about just silicates overall, is there's growing interest in lava worlds with the idea that you'll have silicate vapor atmospheres that then are condensing and being sublimating back into the atmosphere. And so how will that also be affected by treating these different crystalline forms as a function of where they should exist? So that's kind of where I am now. Again, this is very much in progress, preliminary sort of work, but I think we're just in this really exciting era that we actually now have JWST. We can make these kind of determinations because we have access to the silica feature and a lot of detail, both in resolution and just the number of objects that we can observe. So just to summarize, I added in 2 different stable forms of silica that should be prevalent at high temperatures and low pressures. One of them, at least in my chi-by-eye accounting, maybe is a better match to the existing JWST data from WST17b. I think that there's a lot of places to take this that I'm very excited about, and I'm happy to chat with anyone who has ideas and wants to pursue anything that I've talked about here. And overall, we're just proposing that in this silicate condensation sequence, we not only have to consider chemistry, but also mineralogy. It's a very LPL sort of takeaway for this talk. So this is work in prep. Hopefully will be submitted soon. Thank you for your attention. I'm happy to take any questions.
Okay, question.
I was trying to think of something more interesting to ask you, but it did pop out. I was wondering your fits to that point that you showed in the blue and the pink. There was like a point adjacent to it that seemed like it was too low, and I wondered if you could comment on that. Yeah, so like you're saying that the
This
blue
one?
point fits the like peak very well, but what about the point to the
This
left?
one?
Yes.
Yes, that's
Mhm.
that's why I think I need to actually run a chi-squared against this and not
Okay.
squint, which is what I've done so far.
Okay.
With the blue, yeah, definitely looks better.
So I have another question. So here you focus a lot on the dust, right?
Mhm.
But there are there also emission from gas?
Yes.
Yes. So do you have to fit everything together, and where are these gas features?
Yeah, so this is water right here.
Mm.
Yeah, so no, I
Yeah,
was
basically
wondering-
these are both water bands. And so yeah, I haven't done anything to the fits in terms of the gas phase chemistry. I'm just trusting the Grant et al. Best fit and using that kind of to hold everything else the same and just isolate.
Okay, so that fit subtracted the gas species, right? Because otherwise you would need to fit them together, right? The gas and the dust.
But you have to know the gas
Right.
really well, subtract it.
Well, but I mean, what I'm saying is that, you've got to do them
So
together to be sure.
So, I'm essentially just doing the same thing as they have done here. So the different contributions are these different colored lines, and then just in place of the SiO2 here, which they use as quartz, I'm just putting in the optical properties of the different polymorphs.
But then you fit spectrum which subtracted the rest. I mean, otherwise, you see my point.
I guess.
I mean, yes, if I were doing this truly properly, I would rerun exactly this whole grid. Because it maybe would slightly change the,
Or you subtract the component from your spectrum, the gas components, and then you fit only the dust. Right?
yeah, I mean, that would be the other way of doing that. Yeah, I mean, I'm sort of just getting to that step.
Yeah. No, I was just wondering because otherwise, right? I mean, you were pointing out a little feature next to the peak, and that is also affected by water.
That's true. Yeah, because you're still very much in the water band here.
Okay, Everett has question.
Yeah, this is great work on the mineralogy. Thanks. I was wondering if these polymorphs solve the mystery you talked about with WASP 107b of where if it has silica in the atmosphere, it forms really deep, and then how does it get so high? Does it help with that mystery at all?
I don't know yet. I've basically given it exactly as much thought as you have right now. And that I've pointed it out and thought, that's interesting, but I haven't done even sort of back of the envelope calculation, just because again, you are forming it so very deep. At least, if you believe this particular pressure temperature profile that again is just taken from the paper, with assuming that it is a 10 times solar atmosphere, this is the condensation curve, like that's happening. 20 bar, 30 bar. And then, it has to get transported all the way up here and not change phase, have something else happen with it. So I don't know that it actually solves the mystery, especially since by the time you're measuring the spectrum, you imagine you're sort of in this regime, which is quartz. But yeah, I think you still have to invoke some pretty high interior temperature, and you still have to invoke pretty significant upward mixing to make it work. So I don't know that it's solving the mystery so much as adding more complexity to it.
Okay, thanks.
Sam Crossley from Yoko.
Yeah.
Author. Sam, would you like to ask a question?
Or explain either way.
Yeah, or explain, right? I think you need to, unmute, Sam's on mute. I can't hear you.
I don't think Sam joins the
Yeah, I don't
audio.
think-
Oh, you
Join
didn't
the-
join the audio. Can you, if you cannot join the audio, can you then
Type in the chat.
type in? Yeah. Oops. Yeah. So ready. Okay, now you can read that.
So Sam says, the tritomite fitting looks promising to me. At these temperatures, you can get coexisting tritomite and cristabolite, which could help resolve the peak fitting. The problem with true quartz is that the transition from beta quartz to tritomite and from tritomite to cristabolite is that it's a non-reversible transition. So it can't be quartz if the temperature ever exceeded 850 Celsius. And this is why we have a geologist on the team.
Yeah.
I don't know this.
Cool.
Yay, rocks.
Right. All right, Renato.
Okay, so can you hear me?
Yes.
Oh, great presentation, Sarah. Thanks. I'm just wondering that if you have explored how the inclination of these objects could affect quartz clouds. We recently found that there are more clouds at the equator, silicate clouds at the equator of the of brown dwarfs, and that influence the color that we observe. So now my question is about quartz clouds, how inclination can impact these clouds.
Yeah, so that's one of the things that I think is very promising for follow-up for this. That was one of the places that I immediately went, is thinking about your paper in terms of the polar versus equatorial clouds and how you might be able to apply this to use it. But again, that's not something I have done, but I definitely would be keen to chat more if you have ideas.
Thank you.
Any other question? Any other question from online audiences? All right,
I have a
yeah,
question.
you,
Yes.
Obviously,
okay, go
one,
ahead.
but I want to ask you since you know a lot about this. So, I mean, most of the time, right, when we have these exoplanet observations, we make an estimate. We know almost nothing about these exoplanets, so we make an estimate of the equilibrium temperature. How do these clouds impact that the determination of the temperature? How off the temperature is from the equilibrium temperature once you do the proper cloud treatment as you do?
I mean, it becomes a little bit of a chicken or egg situation, is that you need some estimate of the temperature to do the modeling, which then will infer the clouds. So I think you could build a self-consistent way of treating that. But it's gonna be very degenerate.
Okay, I really appreciate. Okay, thanks.
You mean even a self-consistent modeling is also degenerate?
Yeah.
Yeah, and I never thought about quartz cloud. This is, I feel like, how long can they stay there? I can kind of precipitate.
At some point you think they'd rain out, so there,
You should,
you still have the
right?
whole upward mixing problem to deal with, but that I can't help.
Yeah, so the mixing and the precipitation, it'll look very interesting with quartz, it's kind of heavy, I would think. but
Yeah, quartz is the heaviest.
Yeah.
Compared to all of these different poly.
Yeah, so it will have a really either very good mixing or just precipitation. Quartz, seal quartz. Right, thank you very much, Sarah. We'll have her until the end of the summer, although most of us will be gone by then, but
So Mark points out that in terms of the upward and downward mixing, the cloud model is doing that.
oh, yeah, that's great. Yeah, I never thought about quartz cloud. It was really cool.
But it would be like the snowy clouds thing.
I was guessing about quartz slowing down.
Yeah, and mixing up.
All right, thank you. We'll see you next week. Like one more talk next week by Leo Krabs. So we're gonna meet in Stuart. Thank you.